Yeah.
Go ahead.
Okay, thanks, Tracy. Hi, everyone. Thanks for joining us today. Like Tracy introduced, my name is Jose Wadham. I'm a regional sales manager at Vibro-Acoustics. I work with manufacturers reps like Holden Associates and provide technical and sales support. I've worked in the field of noise and vibration control for approximately 10 years now, and I live in Ottawa, Canada. Today, I hope to show you a proven approach to noise and vibration control to add value to your projects in the form of space savings, energy savings, improved air quality, and most importantly, a reduction in total cost. From what I understand, I have a virtual room full of designers and engineers. So yeah, hope that this can be of service to you. So a quick introduction, we'll have a quick overview of the presentation. I'll have an introduction. We'll talk about why noise problems exist, what to look for in a noise problem, noise paths with an RTU example. We'll talk about two common problems, which are breakout noise and environmental noise. We'll look at environmental noise solutions for air-cooled chillers and generators, and then we'll summarize the systems approach. So for the introduction, I have a couple of questions here for you to ponder. So what types of projects would you think to incorporate vibration control? What types of projects would you incorporate noise control? So I assume the types of projects that came to mind were performing arts centers, TV and radio studios, libraries, and churches. There's an obvious need for all types of noise control for these buildings, HVAC included. For most of these projects, though, an acoustical consultant would be brought on board. But what about all your other types of projects? The need for noise control extends further than the noise critical spaces from the previous slide. Everyday structures should be treated for noise and vibration. Structures like healthcare facilities, educational facilities, lab, science, and pharmaceutical buildings, data centers and cogen facilities, stadiums and sports arenas, residential and mixed use buildings, and any other building with outdoor lot line requirements. So another important question would be where to apply noise control. Most specifically, which pieces of equipment would need noise attenuation. So this is a brochure that we have on our website. I highly recommend you guys check it out. It's a all-encompassing schematic. I'm going to run through a couple of the items shown in here, but yeah, you can find it on our website. So first, looking up here at the cooling tower, you can kind of see, it's kind of hard, but there's an acoustical barrier on the left there. There's an intake and discharge silencer with some vibration isolation. There's a T-shaped silencer there under the roof. We've got some self-supporting stack silencers, an air-cooled condenser on the roof with a vibration isolation curb and discharge silencers. Over here on the right, you can see a generator with a transitional discharge silencer on vibration isolation and on a floating floor. We've got some fume hood silencers in the lab. There's some just straight silencers on a duct on a suspended piece of equipment. Elbow silencer here with mold block in the mechanical room. We've got a crosstalk silencer between two rooms. There's the sill throw distribution system in the library at the bottom right. And we've got the mechanical room here just with various vibration isolation and noise control products on all the equipment. And finally, some circular silencers on a axial fan. So that's just a quick summary there, a good tool to use, but let's ask ourselves, why do noise problems exist? To answer this question, I will refer to possibly the most influential book on noise and vibration control. You might have heard of it. It's called the Practical Guide to Noise and Vibration Control for HVAC Systems by Mark E. Schaefer in conjunction with ASHRAE. In his analysis, he describes three main reasons for noise problems in HVAC systems. Today, we're primarily going to focus on number 3, which is components were selected but not integrated properly. However, before we get there, let's address item number one, which is dismissing noise control during the design stage, or item number 2, which is post-design cost cutting, aka value engineering. So Vibro-Acoustics provides design assistance on more than 1,700 projects per year. We have discovered that the noise control scope is less than 1% of total mechanical budget. Sometimes it's far less than that. So is it really worth the gamble? It deserves to be entertained at the design stage, even if you have never experienced a noise problem in the past. It's still worth the insurance. I want you all to think about a project that has gone over budget. I'm sure a few of you have cringed at this thought right now. The truth is that if the noise control portion is typically less than 1% of the budget, then it won't get you back under budget. And what happens if you have a noise issue after construction? It typically costs 5 to 10 times the initial budget to retrofit acoustical solutions. So let's go back to our third answer to the original question, which was components were selected but not integrated properly. This introduces us to the systems approach that Vibro-Acoustics uses. It's proven to solve problems before they arise and cost a lot of money. So the application of the silencer is more important than the silencer itself. That's a quote that summarizes the systems approach that I'll describe in this presentation. So now that the risky business is taken care of, we know that why noise control should be assessed, there's another question to ask. What do you look for? These are the steps that are needed in order to design effective noise control that does not compromise any other design needs. However, this is not what most designers do. Step number 1 would be identify all possible noise paths. For example, airborne, structure-borne, breakout, radiated, flanking, or etc. Step number 2, determine if you're working with indoor or outdoor criteria, such as dBA or NC. Step number 3 is calculate the required noise attenuation for the application. Step number 4, identify specific project requirements such as space, IAQ, budget, and material selections, etc. And step number 5, generate appropriate project-specific bid documents. Now, we're going to explore the ways to select noise control that could fit into the above steps. Most of you are probably aware of 1 or 2 of them. So method number 1 to select noise control would be self-selection using a catalog or a software. Method number 2 would be contacting your manufacturer's rep who self-selects from catalog or software. Or method number 3, which is working with a manufacturer's rep who can provide project-specific analyses. I'm going to explain why the first 2 methods are potentially time savers for designers, but highly discouraged. So we're all aware that ASHRAE provides some basic guidelines to follow for applying noise control to HVAC systems. However, many of them are not practical. In Vibro-Acoustics' 50 years of experience using ASHRAE guidelines, we have identified 14 common noise path problems in HVAC systems. I'm going to go over those in my RTU example later. But I want to talk about these guidelines that are used in creating the catalogs and selection softwares for noise control products. So there's ASTM E477 and ASHRAE. So both of those are guidelines that determine how much room is needed for a silencer to operate as published. ASTM recommends 5 duct diameters of straight ductwork at a silencer's inlet and 10 at the silencer's outlet. ASHRAE recommends keeping the silencer 3 to 5 duct diameters from any flow disturbing device, such as fans, elbows, plenums, or fittings. From these, an issue arises. ASHRAE and ASTM do not focus on how to achieve the noise criteria in the space when you don't meet these conditions, or how to reduce the pressure drop. The engineer is then responsible to somehow design a system under space restrictions, but also meet the NC criteria and at a low pressure drop. Have you ever actually had this much room to work with? I would guess that these days the answer is no, with mechanical areas shrinking. Over 85% of projects aren't meeting these space requirements. Unfortunately, the numbers in the catalog and the softwares are only accurate if the above guidelines are followed. If that's not possible, then the information in the catalogs become completely incorrect. So without an analysis of actual operating conditions, the real noise attenuation is unknown. So we need to know the system's effects. Would you really do this to a fan and not expect it to impact performance? We have the same issue when it comes to silencers. So best practice is applied engineering. So like I mentioned, when the ASHRAE guidelines or ASTM guidelines are not followed, it results in system effects, which can increase the silencer pressure drop dramatically and increase generated noise by the silencer. Here is one of the CFD analyses that we've conducted to figure out pressure drop implications. This is a side view of a duct silencer mounted directly at a duct elbow. From the start, we can see very turbulent air. The test concluded that there was an increase in silencer pressure drop and self-generated noise. To show this in numbers, this silencer has a catalog pressure drop of 0.15 inches at 1,000 feet per minute air velocity. The test measured over 5 times the catalog amount. It measured 0.78 inches at the same airspeed. So a solution here would be to use an elbow silencer to minimize system effects of pressure drop and self-generated noise. Another more proactive solution, though, would be to show system effects in a silencer schedule. Probably the best product out there to avoid pressure drop problems is a silencer schedule. You can use this to specify the pressure drop, including system effects. It would greatly reduce your risk because we are showing that we're applying the silencer and not just selecting it. We also recommend specifying PE stamped calculations, which we can provide to fully eliminate your risk. A quick note to avoid potential pressure drop issues later in a project is to only approve submittals where system effects are shown. So let's talk about the noise paths, which, if you recall, was one of the steps in effective noise control design I mentioned earlier. I'm going to use an RTU example to explain this. So RTUs are the most common HVAC solution for one major reason, because they're inexpensive. Unfortunately, for this reason, though, the typical RTU has high sound power levels. If we break this down, we can see why. RTUs are built lightweight and are made to be as small as possible. They achieve compact designs by including smaller fans, and to achieve higher flow rates, these fans need to operate at very high RPMs. A compressor is also one of the multiple sources of noises from an RTU as well. And unfortunately, there's little to no money left in competitive pricing for noise control. Shown on this slide is the fan sound power levels of an RTU shop drawing. We've got near triple digit values in some of the octave bands. However, typically, where can we find an RTU? That's right over occupied spaces. There are multiple benefits to an RTU placement over an occupied space. Most of these result in less ductwork being required. Energy is conserved by design because there is less pressure drop and thermal losses, lower material and installation costs, ceiling space is saved by ducting directly into the space, and design time is reduced when less runs are required. However, high sound power levels plus an RTU located directly over an occupied space could result in a noise problem and client complaint. In fact, the only reason that an RTU would not be placed directly over an occupied space is out of concern of a noise problem. So unfortunately, we have two problems colliding here. One, the RTU has high sound power levels, and two, the majority of RTUs are placed over a sound sensitive space. So let's talk now about those 14 noise pathways of an RTU that can invade an occupied space. So first is the seismic and wind loading. So any movement caused by either of these events could produce some noise. Next, there's flanking radiated external noise. So that's noise produced by equipment transferred through the roofing material from the exterior. Next is environmental noise. So rooftop equipment and outside air intake and exhaust from mechanical rooms have the potential to exceed community noise bylaws at property lines. Next is ductborne noise. So that's noise transported by the air being supplied or returned to the spaces. Next is aerodynamic system effects and generated noise. The air itself would be producing noise while moving along the entire system. Next would be breakout ductborne noise. Duct breakout noise is sound transmitting through light gauge ductwork and into occupied spaces. This is the noise path that is most often overlooked in HVAC noise control design. Standard silencers can't guarantee to solve this problem because an analysis is required to figure out how much breakout will require and where. This noise path is probably the most common cause of noise problems for designs that already have some sort of noise control measures in place. The next noise path is radiated noise. So this is noise from lightweight construction of the unit or the building transmitted through the ceiling space directly. This could also be noise from a piece of equipment located in a mechanical room and radiated to the occupied space next door. This usually is low frequency noise problems, which are difficult to attenuate. And the last noise path is vibration or structure-borne noise. Structure-borne noise created by vibrations coming from an RTU's fan, compressors, air through the filter bank or the casing, etc., is some of the worst noise problems to have. They're extremely hard to diagnose, and occupants have a much lower tolerance for these kinds of problems. An additional issue is that the heavy vibrations can lead to damage to the equipment and potentially the structure. After we complete an analysis on such a project to determine the noise sources, the aerodynamics conditions, and the project-specific requirements, we then can provide a specific integrated solution for this project. This would include an inlet and discharge silencers and vertical barriers to minimize environmental noise. Typical RTUs have less static pressure to spare for silencing noise radiated to property lines. Intake and discharge silencers are designed to minimize pressure drop and resist corrosion due to the outdoor environment. Noise barriers are also prevent property line noise problems, and they act as architectural screening as well as an effective noise control that do not reduce equipment performance. So finally, though, there's the noise control vibration isolation curb for the occupant space we were talking about. So Vibro-Acoustics NCC VCR noise control curb system is usually integral to the solution. It enables the consulting engineer to reap the full benefits of locating an RTU over the occupied space without the #1 drawback of a noise problem. According to the project's needs, a number of customizable solutions are integrated into the curb. These aren't simply standard options. This provides the engineer a single amalgamated solution to address multiple areas of concern with single source responsibility. So looking at this one here, you can see HTL casing, high transmission loss casing, to address breakout noise. Fit to the system silencers to address airborne noise. Noise control curb barrier to block radiated noise. And anchorage calculation with P stands for seismic and wind loading. So these are a few photos of an installed NCC VCR curb to show that there are no size restrictions in this single source noise control solution. And then you can check out this sample schedule that can be put directly into bid documents. It specifies a guaranteed NC level and a PE stamp to, again, take any noise control risks away from the designer. Okay, so after speaking about some noise paths, I want to concentrate on breakout noise for a few minutes. Breakout is unquestionably the most common noise problem that is missed at the design stage. These are the reasons that a breakout noise problem could occur. So number one would be lightweight construction of the structure, allowing noise to permeate between spaces. Number two would be packaged equipment like AHU and RTUs being installed near occupied spaces. Number three, high sound power levels due to higher RPMs or compressors. So let's take a look at this sketch, and I want you to ask yourself where the best place to put a silencer in the supply side of this system. Many times, the silencers would be placed downstream of elbow fittings in a straight section of duct to simplify installation and lower the perceived cost of noise control. But a bigger issue with this is that it's missing the breakout calculation, even though noise control solutions have been designed. From the time the duct enters the occupied space up to the outlet of the silencer, noise can break out of the ducting. Now, would this system have worked if the ductwork was lagged? It would, if you lagged all of the ductwork up to the silencers, but the costing of lagging of this ductwork would be multiple times that of the silencers. So how would you deal with breakout in that example? You would need to consider all the spaces that are affected. You would next need a calculation for that specific installation, because that would determine where the breakout would occur and how much of it would be happening. Then you could choose the location of the silencer in the system, which is the most important part of the silencer itself. And finally, you would need to determine if high transmission loss casing is required. If it is, then determining the appropriate thickness of the HCl casing to address possible breakout noise. So going back to our sketch, the solution is to treat as close to the source as possible. The best location for the silencer would be straddling the mechanical room wall, but this usually isn't practical. The next best location is just inside the mechanical room wall. In this case, there's no space for that. So the silencer would be located right outside the mechanical room. This usually means a high transmission loss casing would be needed to prevent breakout at the silencer. The T shape with the HCl casing would take care of both airborne and breakout noise paths and ensure that the installed pressure drop of the silencer is within ASHRAE guidelines. So for those reasons, it's impossible to design for breakout noise with a catalog approach. Something more is definitely needed. So I'm going to move on to talk about the common problem of outdoor noise. So environmental noise was one of the noise paths I discussed earlier. Why do we care about environmental noise, though? We often focus on indoor environmental quality with NC criteria. Property line issues, though, are often overlooked. 30% of our business is retrofit work, which is a result of a neighbor or a bylaw complaint. To start looking for potential noise, environmental noise issues, we need to ask ourselves a few questions. So how close is the nearest receiver? Is the equipment at a different elevation than the receiver? What is the local noise code? And is there an acoustical consultant? The common environmental noise product culprits are cooling towers, dry coolers, air-cooled chillers, generators, packaged DX equipment, and mechanical or generator rooms. But how much noise control do you need for outdoor noise issues? The answer is similar to the indoor noise issues. that we discussed earlier. You would need to know the source's sound power levels, the distance from the source to the receiver, and what dBA to achieve. The units used in environmental noise is A-weighted sound pressure levels to approximate what the human ear will hear. A distance measurement is important as well because of the inverse square law of sound. So sound traveling twice a distance will be perceived at 6 dB lower. A last thing to keep in mind is that a reduction of 10 dB is actually reducing the noise in half due to logarithmic laws. So that leads us to exploring a few environmental noise solutions. So starting with air-cooled chillers. Air-cooled chillers pose potential noise issues at the property line in residential and commercial applications. Approximately 20% of the noise generated comes from the compressor. The remaining 80% of generated noise comes from the condensing fans. Good options for noise control are inlet and outlet silencers or an acoustical enclosure. To determine the right solution in a retrofit, something to consider is the amount of static pressure the fans can take. But let's talk about the noise sources within an air-cooled chiller, one of those being the compressor. So compressors mostly produce tonal noise. A scroll compressor would produce a weak tonal noise, which is the easiest to address with noise control. However, a helical screw or rotary screw compressor can produce strong tones in the 250 to 2000 hertz octave bands. This can lead to resonance, which require more intricate noise control measures. So next is the fans producing the most noise in an air-cooled chiller. So you would need to consider that the cooling fans can produce multiple broadband noise. When units are near residential areas, silencers are usually required based on the proximity of people and the lack of space. The circular and rectangular silencers are custom designed for minimal static pressure loss, and they can also be found on the intake and discharge at the same time in some cases. And finally, it's absolutely possible to keep the unit's warranty intact when adding silencers to an air-cooled chiller. So coming up next are some photos of installed solutions. So here's a sketch and the installation photo of an acoustical barrier and discharge silencers. You can see the steel base around the equipment to support the discharge silencer bank. So no weight loading of the silencer bank is on the unit itself. Additionally, the barrier wall is self-supporting and has acoustical louvers to attenuate any inlet air. This is another configuration, which includes circular discharge silencers. The center bullet of the silencer lines up with the fan hub of the fan hub diameter for static regain conditions. And another solution here is an enclosure with integral intake and discharge silencers. These photos are showing the end wall with double access doors. And the inside of the enclosure is tailored to the unit's dimensional allowances for maintenance and servicing. So the next environmental noise solution I'm going to speak about is for generators. So there's a concern for environmental noise, whether the generator is installed indoors due to the intake and discharge areas and or the outdoor installed generators being near property lines. So I'll start with a quick overview on generators. Generators operate with diesel or natural gas fuel, and they're mandated to adhere to some emission standards. They're used in standby or emergency backup power situations, and as we all know, they produce extremely high noise levels. Common manufacturers are CAT, Cummins, Kohler, and Generac. Potential noise control solutions for generators are intake and discharge silencer banks, where the dimensions will vary based on performance and space restrictions. Elbow silencers could be used in tight spaces. There could be acoustically lined plenum Acoustical louvers can be used, which can vary from 4 inches to 24 inches deep. And absorption panels could be installed on interior or exterior walls. And finally, a fully integrated enclosure. I also want to discuss the noise control design challenges for generators. There are strict aerodynamic requirements of less than 0.5 inches static pressure to ensure optimal aerodynamics of the cooling air. Generators require a high amount of noise reduction due to the amount they produce, amount of noise they produce, which can be very costly. The generator room normally doesn't allow for much extra space, and the spaces adjacent need to be isolated correctly from the generator. I've mentioned a few times how much noise a generator produces. The noise levels can exceed 100 dBA in most of the octave bands. The primary source from within the generator are the engine casing, the radiator cooling fan, the engine exhaust, and the turbochargers in diesel applications. In some situations, they're also capable of producing multi-band noise, not only low frequency noise. Like I mentioned earlier, the location of a generator affects everything around it. The concern is for the occupied or noise sensitive spaces beside the generator room. A possible solution is a room within a room construction. This can include air gaps in all facets of the room, like between the walls, under the floor, and in the ceiling. Otherwise, sound absorption panels can be used on all surfaces within the generator room. An obvious solution would be an intake or discharge silencer banks. And finally, another option would be to use a remote radiator to cool the engine while taking the compressor element further away from the occupant area. This is an example project at Memorial Hermann Hospital in Houston, Texas. It involves the brand new construction of an emergency backup system. 6 2.5 megawatt Cummins generators were installed on this project. Vibro-Acoustics designed the intake and discharge silencer banks for maximum attenuation. The requirement was maximum 55 dBA perceived at patient rooms 90 feet away from the air intake and exhaust walls. These are some sketches of solutions for this project. Elbow silencers were used at the generator discharge and incorporated a doghouse with louvers once the air reached the exterior. It was designed to produce only 0.25 inches of static pressure, including system effects. In this photo, there's a human for scale to show the size of these generators. And then here's a few photos from the intermediate floor of the large bank of discharge elbow silencers. Above this was the doghouse with louvers we saw in the sketch a few slides ago. Another sample project is the Philadelphia Data Center. These CAT generators required a transitional discharge silencer. You can see it packed between the unit and the wall there. Specific site conditions needed to be addressed in the dimensions of this silencer. There were 2 columns to work around that you can see better in this photo from our manufacturing plant. The small inlet area was intricately transitioned to the exterior using the space that was available around these columns. Okay, this brings us back to the right approach to noise control, the integrated systems approach. It's where the system is analyzed so that the appropriate solution can be designed into the project, reducing the risk of a noise problem after the building is built. It starts with the acoustic analysis, which addresses how much noise is needed, where the breakout might happen, and all potential noise paths. When the system analysis, then the system analysis analyzes the max allowable pressure drop from the system, when what the potential system effects are, and how much room there is to work with. This process identifies the acoustic needs and system requirements for a specific application so that we can develop the right solution for the job. Potential solutions can be developed using silencers, barriers, isolation, enclosures, plenums, acoustic louvers, acoustic curbs. The media within a noise control product can be dissipative, no media, film lined, or mold blocking. There are many different configurations possible, such as a straight, elbow, T-shaped, Z-shaped, or suited to any possible site conditions. And the aerodynamic features of the noise control products can have flow shaping channels, various modules and baffle sizes, and guiding vanes. And finally, the wind and seismic restraints would always be considered. Remember though, effective noise control is a process, not a product. So to conclude, our application engineering service has benefited thousands of engineers in the past. We find that it has value for all engineers, but provides maximum value for engineers who have not had formal training on HVAC acoustics or do not have the time to continue selecting and applying silencers throughout the life of a project. So if there's any projects that come to mind now where you could use an integrated system approach, just reach out to your Holden rep. So I'm a little bit short on my time, but thank you for your time today. And yeah, let me know if there's any questions.